Welcome along to the next session in this series called Exploring the Solar System. My name is Dr. Alan Wood and I'm a senior lecturer in the physics team at Nottingham Trent University. So what are we going to be talking about today? Well, we're going to continue scaling the solar system and then we're going to start to think about interplanetary travel. So what have we talked about so far? We've talked about Kepler's laws, and Kepler's laws say a planet moves in an elliptical orbit with the sun at one foci. So it sweeps out an elliptical orbit as shown by this red line. It says a line from the sun to a planet sweeps out an equal area in an equal time. So it takes a certain amount of time to go from this point here to this point here, and the same amount of time to go from this point here to this point here. But those distances are not the same, so the velocity will change. And it also tells us that the period squared is proportional to the semi-major axis to the power cubed. So basically the period squared is proportional to the mean distance between this planet and the sun to the power of 3. Kepler's laws tell us what happens, but they don't tell us why. Newton's laws tell us why the planets move in this fashion. And what we also said is we said, based on Kepler's work and Newton's work, it now means if we know the mass of any one body in the solar system and the distance between any two objects, we can scale the whole solar system. In the last session, we talked about how Henry Cavendish worked out one mass. Now, I posed a question at the end of the last session, how do we get one distance? How this one distance was found was by Giandomenico Cassini and Jean Richter. They observed Mars from different places on the Earth at the same time. So in this diagram, the yellow circle is the sun, the blue circle is the Earth, the red circle is Mars, and the dots on the left-hand side are the distant, apparently fixed stars. So Cassini and Richter, they observed the Earth from different locations. They observed Mars from the Earth at different locations at the same time. So if you observe Mars from one location, it appears to be here compared to the distant, apparently fixed stars. If you observe Mars from somewhere else at the same time, it appears to be in a different position compared to the distant, apparently fixed stars. And based on these observations and trigonometry, Cassini worked out the distance to Mars. And that's an incredible achievement. To think that with trigonometry and these observations, you can scale the solar system, and it shows how much fantastic physics we can do with simple ideas applied in a clever way. And this technique is called parallax. So this leads us on to start to think about interplanetary travel. Once we can scale the solar system, we can start to think about how we go from place to place. And we're going to talk about interplanetary travel in this session. Then we're going to move on to results from Venus in the next session and Mars in a subsequent session. So Kepler's laws tell us that planets move in ellipses with the sun at one foci. Comets move in ellipses with the sun at one foci. So it's hardly any surprise that spacecraft move in ellipses with the sun at one foci. So in this diagram here, we've got the sun at the center of the solar system. The blue dot represents the Earth on its orbit. The red dot represents Mars on its orbit. So if we want to go from the Earth to Mars, we could follow an elliptical orbit rather like this. If Mars was over here, we could use a different elliptical orbit. Now, we tend to use minimum energy orbits. If you think about a rocket is mostly fuel. There's very little scientific payload there. It's fuel and fuel and fuel and fuel and fuel. We want to try and make these missions as efficient as possible, so we want to use as little fuel as possible. So we want the minimum energy for our orbits. Now, the gravitational attraction of the sun holds sway across the solar system. We need energy to move away from the sun. That's kinetic energy converted into potential energy. So we need a certain amount of kinetic energy here to be converted into potential energy by the time we get to here, so we can reach Mars. The velocity at apogee, the furthest point from the sun, must not be less than 0. That sounds fairly obvious. We've got to have some velocity to ensure our spacecraft is still moving. So at perigee, at closest approach, there must be enough kinetic energy so we can reach that furthest point. So we need enough kinetic energy here so we can reach this point here. So other orbits are faster. So for example, this orbit here is faster. There's a shorter distance between the Earth and Mars, but we need more energy. We need enough energy to reach this point all the way out here. If we want to go to Venus, well, again, we use these elliptical orbits and we try and use minimum energy orbits rather like this. So this leads us to a question: what's the escape velocity for the Earth? Well, the escape velocity can be found like this. The escape velocity is the square root of 2 multiplied by Newton's constant of gravitation multiplied by the mass of the Earth divided by the radius of the Earth. So we can say that the escape velocity from the surface of the Earth is 2 multiplied by 6.67 times 10 to the minus 11 multiplied by 6 times 10 to the 24 kilograms over 6,378 kilometers. And that gives us about 11 kilometers per second. That's a huge speed. If you think about that, that's the equivalent to going from Nottingham to Derby in about 2 seconds. Now, we're going to think about how we go from one orbit to another. And we're going to use an example here with satellite orbits. So the dot in the center of this image is the Earth. And we've got 2 other dots representing satellites on orbits. Now let's consider moving a satellite between 2 circular orbits. This equation here gives us a force due to associated with circular motion. So F the force equals m the mass of the satellite multiplied by its velocity squared divided by the radius of the orbit. Newton's law of gravitation says the force is equal to Newton's constant of gravitation multiplied by the mass of the satellite multiplied by the mass of the Earth, multiplied by the radius, divided by the radius of the satellite orbit squared. We can equate these 2 forces, and then if we want to, we can rearrange. And when we rearrange and solve for velocity, we get this expression here. The velocity equals the square root of Newton's constant of gravitation multiplied by the mass of the Earth divided by the radius of the orbit. Now, Newton's constant of gravitation is not going to change. The mass of the Earth is not going to change. So if the radius of the orbit changes, so does the velocity. We know that kinetic energy is half multiplied by mass multiplied by velocity squared. So if our velocity changes, so does the kinetic energy. So that's the point of this slide. The point of this slide is saying if the radius of the orbit changes, then the velocity changes. If the velocity changes, the kinetic energy changes. So orbital transfers require a change in energy. So if we want to go from this lower orbit to this higher orbit, we're going to need to give our satellite a kick. Most orbit transfers require a change of energy. Generally, we want to minimize this change in energy and hence the change in velocity. Now, let's let VI be our initial velocity, and VF be our final velocity, and delta V be our change in velocity. As you can write, VF equals VI plus delta V. Let's look at this from a point of view of vectors. Here's our initial velocity, we'll say it's VI. Here's our final velocity, it's VF. Here's our change in velocity, delta V. And here's an angle, let's call it beta. Now, our change in velocity, and hence the change in energy, can be minimized when these vectors line up. If we've got a certain VI and we want to get to a certain VF, well then delta V is going to be smallest when everything lines up, when VI, VF, and delta V are parallel. So our change in velocity and hence the change in energy can be minimized under this condition when VI and delta V are parallel. VI should be as large as possible. It minimizes the delta V we need to get a desired final velocity. Therefore, the minimum change in velocity for an elliptical orbit, and hence the minimum change in energy, is when the satellite is at perigee, when it's closest to the Earth. Earlier, when we're looking at Kepler's laws, we're saying the velocity within the orbit is not constant. It's greatest when our planet is at closest approach to the Sun. For our satellites, the velocity is greatest when we're at closest approach to the Earth. And what we're going to want to do at this point is we're then going to want to give our satellite a kick, and that will move it to another orbit. And the same thing applies for interplanetary travel. If we launch a spacecraft from the Earth, we can then give it a kick to increase its velocity, and it will start to try and move up to a higher orbit. And if we do this correctly, our orbit will take us to Mars. We treat this as a series of two-body problems. Each planet has a sphere of influence, and these are drawn here. The sphere of influence is where the gravitational attraction of a planet is larger than the gravitational planet of the Sun. between large than the gravitational attraction of the sun. And we've drawn these spheres of influence here for the Earth and for Mars. Earth is a blue dot with its sphere of influence shown in a blue circle. Mars is a red dot with its sphere of influence shown as a red circle. This is not to scale, it's just to illustrate the problem. So what we typically do is if we launch from the Earth, we send our spacecraft into low Earth orbits. Then we use a hyperbolic orbit to get to an escape trajectory. And then we can be on our elliptical orbit heading for Mars. If we're traveling to Mars, we're going to need to accelerate our spacecraft compared to the Earth. It will then will be giving it'll we need a kinetic energy that can be converted into potential energy by the time it reaches Mars. So it accelerates relative to the Earth, and we go onto this elliptical orbit that will take us to Mars. If we're going to Venus, well, you can see our spacecraft is going to need to fall in towards the center of the solar system. So that means we're going to need to decelerate it compared to the Earth in its orbit. And then we'll fall in towards the center of the solar system and fall down towards Venus. And in the next session, we're going to start to talk about some of the results from space missions to Venus. And then after that, we'll move on to talking about results from Mars. Thank you very much for your attention and enjoy the rest of your day.